Is my screen visible?
Yeah,
Yes.
Mr.
Okay.
Yes, yes.
Okay. Cool. Yeah. So let me begin with a brief introduction of what Dhyuti is. So this is more or less an initiative started a couple of years ago with the goal of building an open source community to enable chasing hard problems in science and engineering in the AI era. And through duty talks, uh, the goal is to have a platform where we can engage with experts, even budding entrepreneurs and scientists who are trying to solve different hard problems in science and tech. And so we have had two talks so far. One in the climate domain, where there was Dr. Satish, who had spoken about AI for methane detection and methane mapping, and which is very critical towards GHG emissions and determining whether companies are adhering to carbon neutral mission of which is one of the SDGs as well. And then the second talk was by Dr. Santi Adavani, who talked about how physics informed machine learning could be useful for subsurface mapping, which has various implications in terms of, let's say, you have oil fields and you want to detect leakages in pipes. How do you do it in a non intrusive manner with just observation data that's been collected by drones? And physics information learning could be one such tool or a framework that could help solving such problems. So before, inviting another set of experts over the next couple of months, which we have a lineup for, I thought why not present an overview of what physics information learning is, specifically a subclass of networks called pins, and then segue into talks by experts from next month onwards. So today I'll be the one talking about pins. I'm Rahul Sundar. So I am currently a full-time scientist at Verisk Extreme Event Solutions, and I'm also about to complete my PhD from IIT Madras under the guidance of Professor Sunetra Sarkar. So I have worked most of my life during my PhD on physics information learning and high performance computing. So just a quick set of uh, guidelines. Like during the presentation, if you have any doubts, please feel free to stop me and we can keep it as interactive as possible. If you feel this is too basic, we could go deeper into the methodology further if you need, and we could keep it as engaging as possible. So please feel free to stop me wherever you need some clarifications. Yeah. So universe of pins. So I'll be discussing the background and motivation behind scientific machine learning and specifically a class of models called pins. So firstly, I'll go about what are pins. Now, then I define what pins are, what they're capable of. Then I discuss so what. The question, so what? Okay, they're able to solve certain things. So what? What are their implications in across domains? And now they can solve various problems across domains. Now what? What are the implications of that? Now, when they solve such problems as compared to classical methods, what would be the implications of using pins in your respective domains, right? So this is going to be the broad outline of the presentation. So here is a whole art digital twin, which is to set some context. Now you would want to understand for each specific patient, how do you model the pumping volume, whether the arteries are functioning properly, the heart is functioning properly, is it beating properly, is it rhythmic or arrhythmic, and the various cardiological diseases. How do you map all of them and prognose as well as diagnose certain diseases in patients? Now, you could build mathematical models from scratch for the muscle fibers, the electromagnetic pulsations, and also the hemodynamic flow through the arteries. And all of them can be described by very beautiful governing set of equations which form part of your electrophysiology or elastomechanics. However, you could either go about solving these equations with some rigorous computational methods. But however, you would have to calibrate certain properties of these materials, of the blood, and even the nervous system, patient to patient. Now, that is not scalable if you were to do it with typical governing equations, with the standard way of calibration. However, if you were to collect some data, imaging data, you could certainly look at how you can inverse solve this problem and get to the parameters that might be causing various diseases in the body. And another application is where you are looking at a climate digital twin. Now, an Earth digital twin or the Earth climate digital twin would help you forecast weather extremes much earlier than what you are able to do now. At least that's the promise. And AI is certainly getting there very, very quickly. Over just the last 2 years, there have been multiple papers that have spoken about how you could get very good forecasts of key extreme events such as hurricanes, typhoons, tropical cyclones, and whatnot, right? So, and even rainfall, precipitation, extreme precipitation. Now, what the advantage that climate scientists or AI scientists have with regard to building an Earth digital twin is that there is plethora of data sources across different resolutions coming from remote sensing satellites, and then you also have weather stations located across the globe capturing various prognostic variables such as sea surface temperature, precipitation, wind speeds, etc. So which gives you enough data points to calibrate your models, very large models in this case, which could do forecasting, which could do data assimilation, which could also do downscaling, which is basically getting super resolved or high resolution fields given very coarse data as input. Now, all of this, if we are able to solve with AI, we should understand what AI is in the first place. And I'm sure that many of the attendees here already know what it is, at least a key distinction between the subclasses under AI. So, starting with deep learning essentially consists of it's a class of methods which are universal function approximators, specifically the neural networks. And whereas machine learning is a parent class to all of this, which does all sorts of pattern recognition. And then you have artificial intelligence, which is expected to do automated planning, reasoning, cognition, execution, all by itself, given a certain prompt, which is where we are trying to head towards. Of course, there's artificial general intelligence and super intelligence. We'll not go there at the moment, but this is at least a very broad classification or demystification of what AI is. And here comes another subclass of this, which is the scientific machine learning or science for machine learning and science and machine learning. I mean, you can call it in different ways, but it is popularly called SciML these days. So it's important to note that SciML is not a new paradigm. It's been existing ever since there was some physics that you knew and some data that's available to you through some observation or some experiments. And all you want to do is how do you fit your physics to the data that you have, or fit a function to the data that you have. And this is exactly where SciML has always existed, in terms of, let's say, you had the Lorentz attractor, which kind of first discovered that there's even chaos in a system. And thanks to this, the entire chaotic theory was born. And this was certainly based on some form of data and modeling of physics-based modeling of the system. Now, however, let's look at turbulence modeling, where you don't have closures for very, very turbulent flows, which is why you resort to experiments and collect the experimental data of fluid flow fields through some contained experimental setup, and then you try to calibrate certain closure models, which is often data driven. Now, what's different? And this has been done since 1900s, and what is different now is the scale of data, the memory and compute, and of course the advancements in algorithms as well. And typically any given learning machine takes input from some sample generator. It could be your experiments, it could be your simulations, it could be a combination of both. And then you have your initial conditions, you have some system parameters and everything, and then you generate the output, and which goes in as some sort of labeled data or some sort of constraint that the learning machine would have to adhere to, and then try to map the input vector to that output vector, which is your target in this case. Now in SciML domain, you typically have two classes of problems. One is the forward problem and the inverse problem. In the forward problem, you have the system, you have the physics, you know the physics of the system, and you know the system parameters. Like let's say if you take the example of let's say you have the case of gravity. You have a ball falling from a tower. You know that the acceleration due to gravity is g, and you know the value of it. And now what you want to do is, what is the time taken for the ball to reach the ground? So you know the system. All you want to get to is the data, like what your time taken to reach the ground. Now let's say you reverse it. Now let's say you know the time taken to reach the ground. You want to figure out what the gravitational force is and basically get to g from here. And you know the height of the tower as well. So from there you get back to the system. So this is an inverse problem, often called system identification as well. There are different kinds of inverse problems as well. And some review papers on physics informed machine learning are often by folks like Karnadakis, Womo, and Kim. And I would say people who are interested can refer to these papers and learn more about these algorithms. And here's the relevance of pins. So while I described what are forward and inverse problems, you could apply any method to it. But why pins? And I'll come to what pins are, but here is a set of typical inverse problems that we would be interested in. One is design optimization, predictive modeling. Can you model missing physics? Let's say you can only observe a system partially, but what about the things that you don't observe? Can you model them? Can you recover the physics of the data that is missing? And then there's also automated physics discovery. Often when you have experiments, often when you have an research objective, you would conduct an array of experiments. Now you could automate it. Now when you automate it, how do you automate it? There is again a research objective. If the objective guides the automation, and if the experimental process evolves as it collects data and processes the data and identifies or looks at some sort of key performance indicators and appropriately evolves, that's where your automated physics discovery comes into play. And then there is optimal flow control, which helps in better combustion in engines, let's say fuel injection in engines. It could also improve the aerodynamic drag over automotive vehicles and also even aircraft. So these are some examples of inverse problems. And here are some typical pin applications for which there are some references which you can refer to. But here comes a key question, like what are pins now, right? Now, here's where you can build intuition for this. Let's say I am at point A, I want to get to point B, and this is, let's say, Mount Everest. I want to climb, then I can travel linearly, and then I have a hike, right? Now, can anyone say what are the different factors that we might consider? Let's say here the objective is what would be the time taken to reach the top. Yeah? So what would be the factors that I would typically consider? Anyone?
Distance, right?
Distance, yes. Then okay, let's say distance and time, right? So
Velocity, right? Something like that.
yeah, you have distance and you have time, correct? So with that you can compute your velocity, you could compute your acceleration, everything, right, from distance and time. So these are the things that you could possibly measure and consider, right, as factors. But there might be additional factors. Now every individual is different, and their body has a certain set of physiology and physics that governs their capability to climb. And then there's also the physics of the terrain, gravity, temperature, everything. So there's stamina, there's strength, oxygen levels, temperature variation, and so on. So there are other factors that you would have to consider and in order to be able to climb this, right? So I would say the first two are what you could observe, right, which is simple data collection. It's point A to point B. It's a distance and time optimization problem, and you can just look at that. So this would be completely data driven. Now what would make it physics driven optimization is where you bring in these factors into the play and try to optimize your entire journey from A to B, right? So now let's say what would a pin look like, right? So now here is a neural network. So is everyone aware what a neural network is? Like I would like to, I mean, I can't see if you, even if you respond with a thumbs up, so I would like to at least a couple of them to say yes or no, like if they are aware of what a neural network is or is not aware of it.
So we are aware, but it's due to the continuity in the lecture now, it may be a good idea to just briefly mention and give a high level overview so that the continuity is there.
Okay, cool. So here is a neural network. So this neural network could be a feed-forward neural network, a convolutional neural network, any kind of neural network backbone. Okay, so we'll keep it as general as possible. So now here is where you give your inputs to this network, which could be your position at any given time t, your temporal and your spatial coordinate, right? So now this goes in as inputs. Then you have your output coordinate, which could often be the distance covered, then the time taken to cover that distance, etc. And then now you would have to bring in some constraints in order to solve for this problem, which would be how optimally can I, what could be the route that I have to take, where should I take breaks, etc., etc. So if that were to be the problem, on a high level, we should possibly look at the label data, which could come from your smartwatch, such as pace readings, temperature readings, elevation, etc., which could be your label data. And then you have your initial conditions, such as your starting point, your starting coordinate, the elevation at any given at t is equal to 0 and at your starting point. And then the governing physics is of course going to be your Newtonian motion and thermodynamics, right? So these would be your governing physics. So now these can all be expressed in some form of these physics constraints can be expressed as, you know, ordinary differential equations or partial differential equations or algebraic equations or some sort of constitutive laws. Let's say if you're looking at material properties, they often have some sort of constitutive laws, or you could also encode some sort of symmetries that, you know, like you're going to have fractality in some sort of process, etc. And so these kind of constraints, physics-based constraints, can be brought in. And then there are data constraints, which are often your observations or simulation data if you have them, which come as your label data. Then you have your boundary conditions and initial condition in case you're solving PDEs or your partial differential equations. And then you also have your system parameters, right? If you have them. If you don't have system parameters and if you're trying to infer them, then this becomes a hidden or system identification problem. And so what is important to note is that these PIN is often discussed in the context of feed-forward neural networks. So as a result of that, it is continuous in space and time. So you could sample coordinates of space and time from anywhere in the domain. When I say domain, I mean space-time domain. So they can be scattered anywhere in the domain, and you could pick and choose points as per your wish. And on the whole, it gives out a very continuous space-time interpolator or space-time mapper function, which is continuously differentiable. Now, what is important to note is that you could have other variants of these pins with completely different neural network backbones, which bring in their own inductive biases. When I say inductive biases, what kind of prefix symmetries or constraints that the model design itself brings with it. For example, convolutional neural networks has its own set of inductive biases, which are more suitable for image data. And then if you take RNNs, they are suitable for sequential data and so on. So here's a feed-forward neural network. The inputs go in, then there's a feed-forward neural network. You have an output. Then there's automatic differentiation to get your gradients of your output variables. Then you have your data constraints, which is a weighted combination of various components, such as your label data, your boundary condition data, your initial condition data, and some other constraints. And then you have your physics laws, which kind of combines in a weighted fashion the various conservation laws or your governing equation residuals. And then you finally have your total loss, which is a combination of data and physics laws. And then you tend to optimize this with an optimizer, such as gradient descent based methods, which would end up training these parameters which are to be inferred after the end of training. Now, the interesting thing about pins is why it is caught on is also because of its ease of implementation and its flexibility. So you don't need very large set of large lines of code in your code base, and you can just set up a simple neural network. I mean, of course, you would have to define what this neural net is, and then you have one that maps your input to output. Then the other one is where the physics part comes in, where you define the gradients and then define your governing equation, right? And then that's it. Then you evaluate this function and this function at any given t and x values, and then you try to penalize them based on your loss constraint. So all you have to do is define the task that you want to solve, which could be system identification, it could be inferring certain missing variables or missing data, and then you set your input coordinate system and sample coordinates from there. Then you have your output variables that you want to map to. If you have labeled data, well and good. If you do not, then the physics constraint is expected to help you tackle the missing data. Then you have your underlying equations in different forms, but I have seen some papers where they often use pins even for linear equations, which I would say is a very bad idea, because you're looking at a nonlinear approximator to map a linear function, which is very suboptimal. Right? So this is important to note, and which is to say that you don't need pins for all kinds of problems. Only when they are very nonlinear, you need continuous approximators or some kind of quick inference models, quick query models. Pins could be a go-to. And then you have to set up your data set. Typical workflow looks like this: set your data set, design your model architecture and its parameters, initialize them. Then you have your loss function design, and then validate with appropriate set of metrics that you would want to look at to know whether your model is performing well or not. Then you have your optimizer, which is often the gradient descent based optimizer, which are first order optimizers. And then you have an evaluation or monitoring pipeline. Now, while I discussed about pins, the landscape of pins has evolved ever since 2019. The first paper of Maziar Raisi had come out on pins. And this is just a quick look at how dense it has become in just a few years. And there are different kinds of angles with which people have looked at improving pins. One is loss reweighting, like I told you, that there's a weighted combination of these loss components, and all of these components in themselves are separate objectives. So you're looking at a multi-objective optimization problem. So when you have to solve a multi-objective optimization problem, you also have to face the challenge of competing objectives. Like you might want to fit the data really well, and you want to also adhere to physics. You also want to adhere to the boundary conditions. It might so happen that the network learns the boundary conditions very well and the data very well, but not so much the physics. Or it would learn the physics well, boundary conditions well, and not so much the data. So how do you balance the contributions of all these loss components is what your loss reweighting class of approaches to improve pins actually focuses on. Then there are normal optimization targets, like how do you ensure your loss function design is such that the optimization problem itself becomes simpler, right? So, and it becomes better in such a way that you are able to achieve your objective and solve the task in a time constrained manner. And then there are novel architectures to improve the function fitting quality of these networks. And how do you work with really large or complex domains? So I will actually show an example for that as well when I move forward. And there are other learning paradigms. So now let's say I have trained a network. Now it has learned something for a particular domain. Can I transfer the knowledge of this model to another model, probably for a similar application or slightly different application, but if it has learned some features that might be useful, can I learn it? And what is meta learning here? Meta learning is to determine what parameters of what loss function would be very useful for this model architecture, or what this is beyond your typical hyperparameter optimization. Meta learning helps you determine what would be an appropriate loss function for this is one example. What would be an appropriate loss function for your network with, say, any kind of class of hyperparameters? And the other one would be, how do you choose uh, the optimizer? What could be the optimizer that you would want? What kind of loss landscape that you have, etc. So there would be multiple angles that you would want to look at when you're trying to improve uh, the pins, and as a result you have a very rich landscape of pins, which is again continually evolving. And if you're interested, you could certainly look at this archive preprint of this paper. And here is an example, and where I'll discuss possible variants of pins. Now, typically, when you look at spatiotemporal systems, there is a time evolving nature of these systems, and there are multiple scales that you might end up seeing in such systems. So you could have some sort of really increasing temporal complexity. Let's say you have the data that you have collected over time through observations or simulations, are sparse in time for a time evolving system. Let's say you consider the unsteady flow field past the wings of a bird, right? So, or the wings of an insect, or let's say you have unsteady flow field past a car that's maneuvering on a racetrack, and it is very time evolving. And at curbs it could be something, on straight freeways it could be something, and so on. So now the second level of complexity is when you have to collect this data, or you have to model this physics, or solve for some missing data problem, or infer the system parameters over a large if you want to characterize the dynamics of the system, you will have to collect data over a long period of time, which also increases the complexity of training your network, because often when the data set increases in size, either in spatial domain or temporal domain, it brings in additional complexities, and the model might not be able to fit so well to the entire extent of your spatio-temporal domain. And the third complexity that gets added in such systems is when you have rich frequency spectra, where you might either have some sort of periodic dynamics where you have very repeating patterns that can be identified. As a result, the data can be compressed to very low dimensional representations. But once, let's say, it becomes chaotic or becomes quasi-periodic, where quasi-periodicity is where it seemingly looks regular, but it is not. There is a slight time lag that keeps nudging the entire trajectory of the system, let's say, in such a way that it might seemingly look regular, but it is not. It might have some additional frequencies in the system which might have to be captured while modeling. So these three complexities really make it difficult to train pins for such systems. As a result, you have ways in which you could overcome this challenges, where you either have fixed domain size, which is the standard way of doing it. Let's say this is a time domain, and on x-axis, and the y-axis is basically your spatial domain. So I'm only looking at temporal complexity in this case, in this example. So I would like to make it simple for the network to learn. So I have to break my problem into simpler parts. So there are two ways to do it. One is where I gradually increase the time domain. Let's say I break the entire time domain into, let's say, 5 subdomains. And then as I train the model, I keep adding one time slab on top of each other as it has seen data points from each of these time slabs, right? So this is one class of your models, where you're gradually increasing the time domain size and gradually increasing the complexity of your model, of your data or the problem. And then the second class is where you actually reduce overall the time domain size, which is you have actually broken down the complexity of the problem, and you actually solve for the simpler parts and stitch them together. And this is where you have your sequential learning. So you have sequential learning, you have start with time domain 1. Then once you have learned it, you transfer these weights to the next time domain as warm starts, and then you train it again on new set of data points with a warm start, and so on. You keep proceeding and then stitch them together. So these are some of these variants, and this is borrowed from a recent work of mine where we looked at temporal complexities in spatiotemporal systems, and we proposed couple of variants like this, and we compared all of these to see which one works best. And interestingly, the key observation or outcome was that you could break the problem into smaller parts, which is kind of a no-brainer. Like, you break your problem into smaller parts, give smaller chunks for the network to learn, and you also use the help of transfer learning to make it more efficient, and your training time actually reduces significantly by a factor of 1/3. Right? So this is how you could basically frame the need to evolve your pin model for your application. Now, now that I've
Hey Rahul,
yeah
just a small question on the previous one.
yeah
You said stitch them together, right? So
yeah
what did you mean by stitch them together exactly?
yeah stitch them. And I say stitch them together. Let's say I have a model one. Let's say I have domain 1, domain 2, 3, 4, and 5, right? And I have individual networks trained on each of these subdomains. Okay, so I have domain 1 network 1, domain 2 network 2, domain 3 network 3, and so on. Okay, right? So these networks have their own set of parameters. Now, let's say if my entire time domain is 0 to 5, right? 0 to some t, right? So I could break this into 0 to t1, t1 to t2, t2 to t3, t3 to t4, and so on. So there is always a common interface here, joint here, right? So the prediction of the model at t1 for this network 1 would also have to be same as the prediction of model 2 at t1, right? There would be some sort of interface constraints, and if you have enough data, you wouldn't have to impose this on as a in a hard manner. But the idea is, once you have these models trained, you could always stitch these models, in the sense, let's say if I have some t that belongs to this time domain, and I have the limits, since I've already broken the time domain during training, I know what the limits or the domain extents with which I have trained. So the pins cannot handle out of distribution anyway, so I give this as constraint. So if the t is less than, so there's some sort of an if else loop that ensures that if t is falling within this domain, it calls model 2. If it's within this domain, it calls model 4, and so on. And that's how we stitch the model together. Like, so is it clear?
Yeah, got it.
Yeah.
Thanks.
Yeah. So now that I've mentioned that these are very flexible universal physics or science approximators, now we look at what could be some much high impact applications of these. So one is of inferring. So this was an early paper in 2020 where they had some observation data for intracranial aneurysm, and this is 3D data, some imaging data of some scalar dye concentration, and all they wanted to predict was what could be the reference pressure from the concentration of this dye. And they had to get the governing equations of 3D hemodynamics flows, which is nicely governed by your Navier-Stokes equations. This becomes your physics constraints, and then there's a continuity equation, etc. I'll not go into the details of this, but they trained a pin model with spatio-temporal coordinates as inputs, and the outputs being your scalar concentration, then your velocity and pressure. And they had initial conditions, boundary conditions, which of course in this case, this is just a scalar concentration. They had to infer u, v, w, and p, which is a very hard problem because you only have the scalar concentration, and you assume that it also follows typical transport law, and then it is interconnected with your momentum conservation and continuity equations. With this, they train the network to recover the reference velocity and pressure as hidden variables. So this is a very interesting class of inverse problem called hidden physics recovery. And then another use case is in terms of unsteady flow sparse moving bodies. Let's say you have a moving body in the domain, then you have some sparse flow measurements, and or you have simulations, right, or dye concentration like the earlier, and then you could train these model to reconstruct over the entire domain to observe what the wake field would look like and what contributes to effective flight of these natural flyers or swimmers. Then also recover the load generating mechanisms, like how do these birds even generate lift or thrust, and that is where you look at pressure as the hidden variable and recover the loads on the surface of the body. And you could train pins for that and then obtain the flow field snapshots, and also use this trained model as a query model, like, which you could embed on an edge device, right? So once this model is trained, the memory footprint is actually very, very less, so somewhere about kbs. So since it's a simple mlp with, let's say, at most 10 or 10 layers and possibly 150 or 200 neurons wide, then once you have trained, the data set, however, could be of the order of TBs, but your model size is still very small once you have trained it. So all you would have to feed at inference when testing the model is just a set of spatiotemporal coordinates. So this makes it very interesting to save memory and also have it as a query model for space-time on the fly queries that you would want to carry, let's say, on an edge device, or even use it as a way to compress your entire data, simulation data or experimental data. And the other possibilities to extend such pin models is to see, often these models are trained on a single parametric instance, let's say for one set of kinematic parameters or one set of system parameters, or constitute one set of one example. Let's say, for example, this case would be for a single patient. Let's say you collect one data, you have the data which is again in space time, so it's a lot of data points for the model, but it is still a single patient's data. Now ideally you would want to extend this or be able to build a model that can generalize across different patients, and you have to also take in the patient's specific parameters as additional inputs, and that's where you could extend these pins to parametric surrogates and query models, be able to solve more complex optimization problems, and which is where automated discovery and design optimization also come into play. And the other interesting application could be where, let's say, you have a trained pin model. Now it has learned some features in these layers, say hidden features, which we could explain or we cannot explain as well. So now let's say you have these hidden features. What do you do with it? You need not just use it for a single parametric instance, but rather use it as a warm start for similar applications when you're training models. So you have a better initialization, or you have initial set of features to work with, which is where transfer learning or fine-tuning these pre-trained models for newer applications would be useful. And you could also train these models on simpler problems first, and then get some initial warm start set of weights, and then you use it for more complex problems, which is also part of a curriculum learning approach, where you don't solve complex problems directly, rather you break your problem, or you start with simpler problems and gradually increase the complexity. So now this is a very crude table of various domains and various applications of pins. And so there's aerospace and mechanical engineering, there's energy sector, there's civil structural engineering, healthcare, etc. So in the aerospace sector, you have the unsteady aerodynamics, which is one example I showed. Then there is aeroelastic design. So how do you determine the parameters of your wing so that it doesn't face catastrophic failures under severe gusty winds, etc. Then you also have noise reduction in engines, etc. How could you build pins to infer the design parameters that would ensure that the noise levels are below a particular threshold? Then there is energy sector. You have how do you identify materials that could help you with a best CO2 storage, and how do you ensure that the energy conversion and is efficient, and how do you design your wind farm layouts so that your wind energy extraction is efficient enough, and so on. Then there's seismic response, stress analysis, predictive maintenance, healthcare. I showed you one example of aneurysm. Then there's tumor growth prediction, drug diffusion, cardiac models, which is probably the first example that I'd given of a hard digital twin. Then how would you predict localized ocean currents? How do you build closure models for turbulence with pins? And then how do you predict weather extremes, which are often rare events, but they are still possible events. So you would still have to mitigate the risk associated with these weather extremes. So how would you do that? So there are multiple levels of applications, different domains. So all you need is the knowledge of either partial or complete knowledge of the physics governing that particular system. And then you need to have at least some form of data and design your data and physics constraints accordingly. And you would have to, your loss function should be such that it has to be tailored for the loss it has to be tailored for the task that you're trying to solve, like system identification, discovery, or hidden physics recovery, and or a forward problem where you're going from raw governing equations all the way and you're trying to mimic, or you're trying to find an alternative to your typical computational solver, and you're trying to simulate certain conditions or certain field variables using some input parameters. That's where pins could be helpful. All you need is you pick a domain that you work on, find out what are the different uh, physical systems that exist out there, and what is that you are interested in. List down the governing equations and feed it as your physical constraint depending on the task that you want. And that's kind of the broad applicability of pins. Now, however, while I say that pins can be used for this, you can be used for that, etc., there's also a caveat that not every field has actually matured in terms of its adaptation of pins. High maturity at the moment seems to be engineering, aerospace, and energy, where people have built CFD surrogates for aero design and reservoir modeling. And reservoir modeling, especially in the sector of people, scientists from Shell and ExxonMobil have actually published papers where they have used pins for reservoir modeling. And then there's also medium, which is emerging at the moment, because the key reason why healthcare could possibly be in the medium range is because getting data in this sector is actually difficult. However, in the case of climate, you have enough data, but the system itself is quite nonlinear, quite complex, which is why pins are still in a state of evolution here in this domain. And there are also better algorithms. There are better architectures apart from MLPs that you could use as backbones to solve these problems, inverse problems. And what you need to keep in mind is a pin as a class of networks, where the backbone need not necessarily be a feed-forward neural network. It could be anything, but subject to certain physics constraints. So that's the way we could generalize what a pin is. And the low but frontier applications are material design, electronics, semiconductor. In semiconductor manufacturing, there have been some recent publications. Then also chemistry and manufacturing, and very recently, I'm sure you must have seen the paper by DeepMind, where they had used pins to discover unstable singular solutions to Navier-Stokes equation, which is basically bringing them very close to solving the millennial price problem, and which falls in the category of computer-aided math, which is also a very high impactful application at the moment. And now that I mentioned that it can solve various meaningful inverse problems and forward problems, now what are the business implications, right? So different use cases. The key, so you could categorize them into different buckets, put them into different buckets. So one is you could reduce the cost and improve efficiency across these sectors, because let's say we are not looking at replacing CFD or FEM solvers, simulations entirely, but we are trying to build surrogates of the existing data sets or legacy data sets that you would otherwise have collected in your respective teams over the years. Then you could build a physics-based model that learns the underlying patterns, underlying physics of this data set that you have collected, and be able to accurately, or while you often trade off accuracy and efficiency, you would still want to get to reasonable accuracy with these models. So you get to reasonable accuracy of predicting the target variables of interest, which could help cut down your design cycles, which could help improve construction, reduce downtime of certain systems, which is where this brings you closer to your digital twin of a physical system. Then faster time to market, because once you accelerate your design cycles, your product development cycles in some form, you could also accelerate your time to market, and you could get off the runway much faster. And then there is also risk management and compliance, where how do you build safer systems? How do you have seismic safety checks? What do you do about climate risk analytics? How do you bring in regulatory approvals in medtech, right? So when I say regulatory approvals in medtech, so this could be more on the knowledge mining side of things, but where does spin figure in that might be a question, right? So now here, what is important is that when you have any data set that you would anyway have to get to a POC stage for any given a data set, you would have to get your POC